Today's presentation is Stagefright, Scary Code in the Heart of Android.
Josh and Drake. Thank you, everyone. Thank you. Thank you all for coming. Most of you probably have heard plenty about this research already. I just finished the slides literally 10 minutes ago, so please bear with me on that one. There is definitely new information here that's not exactly public, but there's a lot of stuff that is kind of already been talked a lot about in the media and such. So without further ado, let's just jump right in here. So here's a quick agenda to show what we're going to go through today. I have this long sort of history of having really super packed slide decks. So if you get lost, the slide deck will be released. You can always go through it as many times as you like soon. And there's actually, I think, something like 20 bonus slides that I couldn't fit into the time. So here we go. So a little introduction. I'm Joshua J. Drake. I go by JDuck on the internet. I've been doing vuln research, exploit dev for 16 years, and that's professionally. I've also done some for years before that, even on BBSs back in the day. Right now, I work for Zimperium as their VP of Platform Research and Exploitation. So I was also lead author of the Android Hackers Handbook, which we published last April. I believe they have it in the bookstore, and we're doing a book signing tomorrow at 10:30 in the morning with myself and 4 of the 5 other authors on the book. I also founded the DroidSec research group a few years back, realizing that there were a bunch of researchers looking into Android, but they really weren't communicating amongst each other very much. I thought it was important to bring us all together. Previously, I was with Occupant Labs, who is now Optiv, and Rapid7's Metasploit and VeriSign's iDefense lab. So the purpose of this research, the motivation, the driving factors behind me doing this research was to, number one, overall improve overall the state of mobile security, right? Mobile, especially in the Android space, has had a lot of bad rap from a lot of people. It's also got a lot of complications going on and a lot of problems. It's something that when you start researching Android, you learn this very quickly. And so I wanted to do that in 2 ways, both by finding and fixing vulnerabilities, so a very proactive approach, but also to kind of give people a reason to want to do better. Nothing really motivates people in security like a deadline. So deadlines are good. So I also wanted to increase visibility into some of the more risky code in Android. I don't know how many people, but just by a show of hands, how many people have ever checked out AOSP? That's pretty good. It's like maybe a third. It's pretty good. So that's like 60 gigs at this point. That's a lot of code. And I can't imagine anybody reading all that code. I don't think that's possible, not humanly, especially not well. But so I wanted to highlight some areas in Android that could use additional attention. And last year I did a talk here about the Droid Army, which is my collection of Android devices. So I wanted to use that some more, do some good testing with that. When you spend so much time on a project like that, you want to use it as much as you can. So sponsors in this work, a lot of the work was sponsored by Occupant before I left that company, who is now Optiv again. And I've joined Zimperium in April, and they've been continuously supporting me through this entire process. I want to give special thanks to Amir Etemadi. I don't know if he's here. Is Amir, are you here? He said he might not make it. I don't see him. Okay. And I also want to thank Colin Muller and Matt Solnick, who also were very helpful, especially on the MMS side of the research. So first of all, what is Stagefright? I'm sure you guys are aware of Stagefright, the phenomenon of, got to get off the stage right now, right? So, but this is different. You can see here, Dan Kaminsky thought it was pretty funny, and I agreed with him from the beginning. When I first found this code, I was seriously like, who names it that, and why would they name it that? So it's really just a multimedia framework library. It supports a lot of the handling of video and audio in Android, not images. Images are handled by some other code. And it provides the playback facilities for whenever you play back a video, but it also does much more, like extract metadata like thumbnails or the dimensions of a video, for example, or a frame rate. And so it's used quite a bit. So a brief history of Stagefright. So it launched in, so Android launched in the 1.0 days with OpenCore as their media engine. At some point during 2.0 dev, they decided they're going to rewrite it from scratch in a new project called Stagefright. So during Android 2.2, they actually supported both engines and shipped both engines on all the devices. And at that point, they controlled which one was used with the system property. When I looked at the devices in my Droid Army that ran 2.2, all of them ran with Stagefright enabled. I think during that time it was widely recognized that Stagefright was much more optimized and quicker code and more efficient, and so everybody was jumping on to use that. In Android 2.3 Gingerbread, which was quite a long time ago, I don't have the dates here, but I think that was 2010 maybe. So they shipped with it as the default, got rid of OpenCore entirely, you couldn't go back, and they've had that ever since as the media library that they use. So a side note, it's also used by other people. The Mozilla guys that work on Firefox made a fork of this code and put it into their browser. They ship it on all versions except for Linux, where they use GStreamer. And they started in 17, so that's quite a while ago as well. So why Stagefright? Why look at this? I mean, besides the name, right? The name's probably enough reason to look at it, but why else look at it? What I found when I did some deeper research into how the code is exposed, and I'll talk some more about that, was that it's exposed by multiple attack vectors. And I found that one in particular was very nasty, that being MMS, because it required no user interaction at all to trigger the code. Also, it's written in native code, it's C++. Let me try to stop saying, how about that? So it's written in native code, C++. So that means it's a little bit more prone to memory corruption issues and other sort of mistakes that happen at that level. And because it's C++, it's also a little bit easier to exploit. C++ builds in a lot of different function pointers into the language, and they use them quite a lot. So that makes things a little bit easier to exploit sometimes. So also, if you look around for people talking about media on Android, and you'd go look on our Reddit, Reddit's our Android, or the AOSP bug tracker, or just random sites like some of the Android forums, you'll see all these people complaining about how their device's battery dies instantly, or the phone keeps rebooting, and then if you read the whole threads, you'll eventually read that it's all happening because you have corrupt media on your device. So I was like, okay, that's pretty bad. I have to look deeper there for sure. And also recently there were some related publications about fuzzing this media code. So I'm just going to go through these quickly. There was related work here in April published by Alexandru Blanda and his QA team from Intel. They released their code. It's out there. And one of the interesting stats from their presentation was they fuzzed the media stuff, and they ended up with 11.5 terabytes of corrupt media files that would crash this code. They reported all of that stuff in some form to the Android security team, who they said accepted 7 security issues, but I only saw 3 ever get fixed, and we'll talk about those a little bit later. So. Other than that, there was another paper that was released at the Asia Pacific CCS this year, and it also talked about fuzzing different things on Android, but they had a nice focus area a little bit on the media stuff. And then if you go way back, and this was focused on OpenCore, not on Stagefright, but Charlie Miller's original Android talk that kind of started Android security research in the public, also was very related, although, again, not Stagefright. So, again, Stagefright is big. It's not huge big, like the Chrome code base or something of that nature. It's certainly a small part of AOSP, but it does support a wide variety of formats. And in order to focus my research to make things more efficient and to be more effective, I decided to focus on just one file format, and that was MPEG-4. So the rest of this talk, when it talks about file format or any bugs or anything, it's all going to be MP4 focused. Let's go a little bit into system architecture. Here's an overview of Android's architecture. It shows the application framework being at the top with the Linux kernel being at the bottom, and you've got kind of everything in between. The interesting part here is that they call out media server specifically, being here in the Android system services, and they also call out system server, which is a very important process on Android. So Android is very modular, so they've tried very hard to use privilege separation to run different programs under different UIDs, the user IDs, and with different privilege levels, and then they talk to each other through inter-process communication, usually binder. So they also use a sandboxing, and then I put quotes around it because I don't know if I am like fully on board with calling it a sandbox, but it's called sandbox a lot throughout the documentation and such. And it basically relies on this separation between users. So if you have the media server running as the media user and you have the system server running as system user, then they have some isolation from each other. And also when you install applications on Android, they each get their own user ID and have to be separated that way as well. So libstagefright executes inside the media server component. So it runs in the background on every Android device that I've ever seen. I've never seen an Android device without media server. That's another reason why I looked into it. Back when I got the Droid Army, one of the things I was doing was looking at all the devices, what is common between all these devices. And media server definitely stuck out as one of those. So it's a native service that starts from init. So when the kernel starts up, the first thing it does when it's done initializing is it runs the init process. The init process will then read this configuration file and launch all the services that are set to be launched there. An interesting thing to point out is that when a program that's started by init crashes, init will automatically restart that thing, basically indefinitely on Android. I think on some other systems like Linux, like Ubuntu or something, if your process is crashing over and over that's starting from init, init will actually say, hey, this thing is messed up, maybe we don't want to keep restarting it. They'll have an aggressive back-off time on it. So let's talk about privileges of this device. I mentioned that it runs as the user media. This is a Nexus 5. This is from the init script again. So you can see here, apart from running as the user media, it also has access to the audio, camera, internet, Bluetooth administration, bandwidth accounting, DRM remote procedure call, and also the media DRM group. So what these groups on Android let you do is talk to a lot of different endpoints. So basically they're opening a bunch of attack surface. If you're able to get into this process, you have all this additional attack surface exposed to you, but you also have all the legitimate functionality that those groups will give you access to as well. So the audio group is, for example, used to limit access to the devices that the kernel exposes for dealing with the DSP. So if you want to record audio, then media server is able to do that. If you want to take pictures, media server is more than likely able to do that. If you want to connect to the internet, how convenient, it's able to do that. So there's more. So I did a survey on the Droid Army. I had 51 devices plugged in at the time. I think I have almost 100 devices at this point, but they're not all plugged in all the time because I need more time to do some refactoring on that. So I surveyed 51. The breakdown here is by OEM. I don't even know what I'm trying to show here. There might be something missing. Okay, this is the number of groups, on each device. So on Google Nexus devices, that can't be right. I am gonna have to take a note on this one and look at that one later. That doesn't look right at all. Bear with me. So let's look at some more survey results. If you look at, again, we talked about all these things, what they can do. Here's them commented out and explained, so you can look at it later. And I kind of hinted on what you can do with some of these. And the worst of it is, at this point, if you attack this process successfully, you can already just stream the microphone straight to yourself. Like, if that's what you want to do, you just write like a little bit of code, read from the DSP, send it over the internet. That's it. So looking closer at the Droid Army, if we start to take the groups and break them into like unique number of devices with that group, you end up seeing that most of the devices, you can see here the count on the left, 51, so all of the devices had these groups. And with this 33 devices had the bandwidth accounting, 33 with DRM RPC. You have 27 devices with the system group. So the system, that's rough, that's like over half of the devices I surveyed. The system group is very crucial group on Android, to the point where it's basically one level below root. So if you have the system group, you can basically get root really easily, usually. But it still would require another bug, a very minor privilege escalation. But even without that privilege escalation, say you don't want to bother getting root, system server still is the thing that approves permissions for apps. It's the thing that lets you do basically everything on Android. Almost everything goes through system server in some way, especially the things that are important for security critical decisions. So then we go down to the next one. We've got graphics devices with 20, graphics group with 20 devices. Now, the graphics group has been used numerous times in the past to exploit privilege escalation vulnerabilities in the Linux kernel. So you don't normally get this group from an app. You can't ask for this group in an app. There's basically like not many ways to get this group. This is one of them. And then sometimes you're given this group through an ADB shell, although that's a lot different attack vector than this is. So I don't want to go into the rest of them, but you can see there's a breakdown at the bottom there. There's two that are really weird. There's 4 devices with the shell group. The shell group is normally only assigned to the ADB shell process when you do ADB shell into a device. And it's mind-blowing to me why this process would have that access. And then the radio group. So if you had to rank all the groups and all the users on Android, like you've got kernel and then you've got root, then you've got system, next one's radio, because radio basically has access to your phone. It can send, SMS, it can make calls, it can hide your calls, it can it can do a lot of things. It's a very powerful position to be in with that group. So let's recap a little bit about this before we end this section. libstagefright processes its media stuff inside the media server process, which runs privileged, potentially even with system privileges, and it automatically restarts whenever it crashes. There's additional attack surface, even compared to having an ADB shell. So let's talk about attack surface itself. And when I talk about attack surface and vectors, generally a surface is what I will call the code that's beneath the vector. The vector is the way you get to the code, right? So kind of at some point, the libstagefright library in this case, that line becomes the attack surface, and everything before it is just part of the vector. So locating the attack surface. This is how I figured out where the code was and what was going on, right? I just started up the video player to play a video with the debugger attached, and I looked at the backtrace to see where things were what the functions were, what's important here. And you can see here all the different functions. So when I did that, I looked even closer at each function, and then I started to see kind of where it was calling into things. Here you can see it's calling set data source on line 2127. So we look at that function, and then we see it's calling this extractor count tracks. So that ends up calling this function in the MPEG-4 extractor class called count tracks, which then calls read metadata. So simply counting how many tracks are in this video would directly call right into Stagefright, the parse chunk function. So the parse chunk function is it's the primary attack surface for the MPEG-4 parsing in libstagefright. It handles the dispatch for basically all the 4CC codes that are handled, and it's implemented as a recursive function. So whenever it sees an atom that is supposed to have like a collection of atoms inside of it, it takes that data and then calls itself again with an increased depth. So I did a little survey of different versions of Android to figure out how many atom types are supported, and I came up with 80 on the lower end and 140 on the newest devices. So this code has been continually developed over time, and it has more now than it did before. So now let's talk about some of the attack vectors. Let's talk about how do you get into this code as an attacker. Like, the surface is great, you can tickle it and play with it, but if you can't actually get there as an attacker, it's pretty worthless. So I used this methodology to enumerate what the attack vectors were, with my goal being how can I get my media files into this code. So, one thing I did a lot was I would set breakpoints into this code, and then I would do things like open videos, look at the gallery, like attach one to an email, like send myself MMS, all these things. And those are quickly showing you if that code's being hit or not. The only note I'll add is if you do use the parse chunk function as your breakpoint, you'll get a lot of noise because it does recall itself recursively. So try to break more on the read metadata function instead. So the problem with this kind of methodology is that it depends on you knowing every way possible to do it anyway, right? How do you know that there's not some weird esoteric way where you can maybe bump phones with somebody and get a media file? Or I don't know. There's a lot of ways, right? So you don't know them all, and so the only way to really figure them out, and it's may change from version to version in Android even, is to just read through the code and figure out what's going on. So the idea is to find all calls to the function, see if, ask yourself, hey, can attacker's data reach here? If you don't know the answer, then you continue to track backwards until you find, that place where it's read it from the network and then pass it along. So again, I mentioned the modularity in Android. It does complicate things. During looking at the code that is kind of coming between the attack vector and the attack surface, in one case I saw a code path that called in and out of Java code back and forth 3 or 4 times. I don't know what's going on there, but that's what was happening. So also it's object-oriented code, so that means you have to pay attention to the members of classes, you have to pay attention to methods. You can't just, it's not as easy to grep for things. So you have to be mindful of that, and also the lifetimes of some of the things. So I mentioned also how things are connected with IPC on Android. That's another thing that can complicate things. Sometimes you'll be reading some code, it'll read some stuff from the network, and then it will just kind of throw that up in the air, if you will. It'll broadcast an intent and say, hey, something, deal with this, and then something else will pick it up. So you have to be able to figure out what's going to pick it up and then continue your auditing from there. And another thing that complicates things is some vectors may be through apps that are closed source. A great example being Hangouts or Google Plus, or just pick one of those closed source Google proprietary apps, or even third-party ones too, or those from the manufacturers who may create their own. So in my opinion, this is still the best possible way to learn all methods. I mean, you really have to do a lot of stuff. These are the things that will complicate it, but at the same time, without consulting the code, you're not going to find conclusively what the answer to that question is. So the first vector that I found when I was doing the research was just using the video tag in HTML5. I was like, oh, HTML5 is cool. I better try this video tag because I haven't done HTML since 4.1 or something. So I tried it, got my cat picture that I just sent myself an MMS with a link, like, hey, check this out, boom, and it did hit the code. So then I was like, oh, I remember back in 2009, 2010 timeframe, there was a guy who was like, Thomas Cannon, he was like, hey, you can make Android download files automatically by just saying, hey, the file is an attachment, not an actual, here's the file. And then if you do that, you can see the progression here. It's a different link. Well, I think it's just, sorry, excuse the image. It was a different link in reality, but I just used the same image here. You can see in the second picture the different link there at the top, and then it's just an iframe pointing to, a Python script that spits out the headers saying it's an attachment. Oh, and that's exactly what you see. The toast at the bottom, the downloading in the oval, that disappears pretty much right away. So it's kind of hard to get the screenshot. But at the same time, the download has already happened. And if you look to the right, the final image, you see what you would see if you go home, app drawer, and then touch the downloads thing. Or if you swipe down from the top, look at the notification for the download and touch it. Now, this attack vector, here, let's go ahead next line. This attack vector, all the downloads are happening in the background. Android has a whole subsystem that's called Download Manager that's provided to apps and everything else to kind of say, hey, I want to download something, but I don't want to do the downloading, so why don't you do that for me and let me know when it's done? So that means that downloads are happening in the background, even in the browser. There's no prompting, so you cannot even, and unfortunately, you cannot say, hey, I want to be asked if I want to download files. It's just going to download it, whether you like it or not. So feature requests, John, I'm looking at you. You can like rebroadcast it for me. So the behavior has been abused in the past, right? With Thomas Cannon's data stealing attack, but also on Safari, there was a big deal, a big press article back in the day about Safari carpet bombing, where somebody could come to your website, you could just like spam the hell out of them with files, and then your desktop is just filled with files, because the default for Safari is to just save everything to the desktop. And I don't know, I don't use Safari, but does anybody know if that still is what happens? Nobody? Does it still save automatically to the desktop? Anyway, it's unrelated. So testing shows that it processes media as soon as the download is finished in pretty much all cases. There are ways to call into that code that you can tell it not to scan the media, but when I look at Android's code in the places where they call in there, they typically tell, don't scan it, and then when they get the notification that it's finished, they go, hey, scan it. So that's interesting. There's a link here if you want to read more about the download manager as well, and there's a long section about this stuff in more depth in the bonus slides of the deck here. So enter the media scanner, right? So at some point I'm reading the code and I'm like, hey, what is this thing called media scanner that they keep calling into everywhere all over the place? It's called into by the download manager directly if you say so, or it's called into by those apps where they're like, well, the download's finished, let's scan it. So I read about it. It's actually somewhat documented in the documentation pages. And mostly they document what's called the media scanner connection. And they also listed media mounted and media scanner scan file intents in the intent documentation page. So I thought those were very interesting. Like I can just send an intent that will just scan a file or scan, let's say, an SD card or a whole directory or however you want to do it. This thing extracts the metadata, uses libstagefright, so it's hitting this attack surface. So with our new understanding, we can go back and look at more things like, okay, now we know the media scanner, we know what it does, and we know about these intents. Like, where else are these things being used? And we just continually learn more things basically to grep for, and then we go grep for them, which is great. So when we do that, we find tons of attack vectors. We find a multitude. We find MMS coming over the mobile network. For client side, we see the browser that we mentioned and the downloads we mentioned, but there's also email attachments. When you receive an attachment on Android and email, it doesn't automatically download that, but if you say, hey, I want to look at that, it's going to download it and scan it. So you also have physically adjacent things, right? Like I mentioned, bumping your phone with somebody, also Bluetooth, or if you transfer vCards with anyone. I don't know if anybody's ever actually used vCards, but they're hanging around somewhere in there. So physical, there's also SD cards. So if you put some malicious media on an SD card and shove it into somebody's phone's SD card slot, it will immediately mount that SD card and scan all the stuff on it. Very convenient. Also, you can use a USB OTG drive if you have, and that's OTG is on the go. And so basically what it means is it tells the device like, hey, why don't you stop being a USB device and start being a USB host, and I'll give you my USB drive. So it doesn't work on all devices because of hardware support, but that's also a very legitimate attack vector. So since Android 4.0, they also have a mode called MTP and PTP, and that's the Media Transfer Protocol or Picture Transfer Protocol. Those are created by Microsoft, but that's irrelevant too to this talk. But so anything you upload to a device when you're connected through these modes will also be scanned. And finally, the gallery, when you open it, it scans it. Or anytime you see any sort of thumbnail or any sort of thing happening on screen, it's still going to continually scan it for some reason. I thought if you scan something and put it in the database, then you'd probably have it in the database. You can go get it there instead of just keeping scanning it again. But it may be faster to run Stagefright code to scan that media and get the information you need than it would be to actually go and hit the database endpoint. So in total, I counted over 11 attack vectors. That may vary between devices. My test device was a Nexus device, Nexus 5, and all of the auditing I did was purely on AOSP. It was no other code bases whatsoever. So ask yourself, do you use any of these to talk to any people you don't trust? Or can anybody talk to you that you don't trust through any of these, whether you talk to them or not. So the scariest part, and this is the thing the media picked up on the most, and I think it's the most dangerous, the thing we're seeing people make kind of drastic changes, like I was notified earlier that T-Mobile in Germany is actually disabling MMS on their network. Pretty drastic, but maybe warranted. Maybe they determined they had a lot of really old Android devices. So it's automatically processed in the Hangouts application, and also further testing showed that the Messenger application that everyone missed from when Hangouts became the default is now in the Play Store. That one also triggers pretty aggressively this code. So in Hangouts, when the MMS message comes in, by default auto retrieve is on. There's a setting called auto retrieve. So it'll download the media and then scan it right away without, your screen can be off. It doesn't even matter. And I'll show that later. So exploiting it could get you all those privileges we talked about before. And through MMS, you don't even have to worry about them touching anything, or their phone could be in another room, or and I didn't put this in the slides because I just kind of thought of it last night. It dawned on me again. It's one of those things comes up in conversation or such. MMS is transferred through what's called, I don't know what they want to call it. I don't know what they call it, but it's meant to be a reliable communications mechanism. So basically, if I send you an MMS and you turn your phone off because your phone's blowing up with these nasty MMSs, sure, your phone's off, that's great. But you turn your phone on, this carrier network held on to all those MMSs for you. They waited for you to come back and get them. So you turning your phone off isn't even really a great mitigation either. It's kind of crazy. So one thing so I mentioned silent here, and the reason I say that is because the code, all the vulnerable code is triggered and the exploit triggered before the notification of an MMS ever hits your device. So you could theoretically, and it'd probably be a significant amount of engineering work to do this, but you could develop an exploit such that the payload would clean up all that mess and stop any of that from happening. Delete the MMS, all the things, and you wouldn't see anything at all, even when you were looking at your device. And that freaks me out. I don't know about you guys. So the big thing here is that it's you need a phone number to attack somebody this way, but a phone number is a 7-digit number. Area codes are fairly predictable. You don't really need to brute force all of those. And prefixes are actually queryable through a website. So at some point you can limit that down to a much smaller number and just hit everyone if you wanted to. So where does it work? I mentioned the Hangouts application. Somewhere along the line, when they introduced Hangouts as a default, they removed the original messaging application, the one with the little green square with the happy face. And so I mentioned this. Okay, let's keep going. So if you guys have MMS, right now, you should take your phone out and you should turn off auto retrieve if you have not already, because it will save you from the nasty. It won't save you from everything. You can still get spammed with MMS. You can still get lured to click it. You can still get lured to a link. You can still excuse me, you can still, I can't even say that. Thank you, guys. So you can still get SD card inserted, if you will. There's a lot of ways still. So it's not a silver bullet, but it absolutely makes the nastiest thing. It will hopefully, if you have a really old device, which I hope you upgrade, it could prevent you from being the propagator of a worm, possibly. So I mentioned this before, the vulnerable code is triggered very virally, if you will. I like to use that word for some reason, and maybe it's the wrong word, but aggressive. It's similar to the old days when you would see sort of an image file that you save on your desktop, and all of a sudden the vulnerability triggers, and then things get really ugly from there. So, for example, rotating the screen, every time the activity in an Android app is redrawn with media showing, it just scans it again. So let's keep going. So are there any other vectors? I don't know. I haven't looked at everything. I can't look at everything. I got this question a lot on Twitter, is WhatsApp affected? I have no idea. I don't use WhatsApp. Is Facebook Messenger affected? I have no idea. I don't use Facebook Messenger. Go on, and I haven't tested them all. So in general, you can go and say, if an Android device is allowing you to view media from any untrusted person, then it's probably affected. Yeah. No, excuse me. So, here's some other ideas. If you guys decide to look into this stuff and you want to learn, you manage to find another attack for, I'd love to hear about it. Something cool like that is always fun to learn about. So let's talk about finding the bugs. That's juicy and fun. So basically, we have a discovery methodology that looks really dumb, and I'm going to go kind of turbo fast right now. There's nothing like rocket science right here. You write a fuzzer. The methodology maybe is a little rocket sciencey, is a little advanced, but writing the dumb fuzzer is like, seriously, it's a 5-minute, like 5-line Python script. That's fine. You run the fuzzer, let it go, and while it runs, read the code, wait for a crash. You get a crash, go read the code near the crash, because like it's bad code. It's got to be bad, right? Well, first, what caused the crash, and then like what else could happen in that code, because maybe something bad is there. So you just repeat that until your brain is fried, and then you go sleep and try again the next day maybe. So the first round went something like this. We focused on MP4. We didn't really build a corpus, a big optimized fancy corpus of test files. We basically had one file called meow.3gp. It's just the cat video you may have seen in the other pictures. It's really a simple video. And we just started with that. So we ran it for about a week on a bunch of Android devices. I did not run it across the whole Droid army by any means, but it was like we picked a few select devices and we fuzzed on that. We got 6,200 crashes in 1 week. Unfortunately, when I looked into these crashes, one by one, bucketing them into like similarity and all that stuff, what I found was there were about 20 unique bugs, but they were all really, really lame bugs, like null pointer dereference, or like there was an assertion where they're like, if this number is not 1, then we like throw our hands up and crash, stuff like that. However, when I was in the code, I started looking around nearby, which is why I recommend everyone does that when they're looking at this their analysis. And I found about 5 memory corruptions at that point. And these became these 2 CVEs, 1538 and 1539 from this year. So 1538 is actually 4 different vulnerabilities, but they're all wrapped into one CV because of similar root cause and lifetime. So on the second round, I decided to try out American Fuzzy Lop. I thought that was a really cool idea, like coverage-based fuzzing is really cool, and the way that this is implemented is quite clever. And so this fuzzer kind of gravitates towards exercising new code. The main goal, I think, behind creating AFL was to generate a corpus for other fuzzers to use. That way you optimize code paths, not by finding all the files you can and testing to see which ones are the best, but by creating files that will actually reach the most you can. So the second round methodology is a little different. So I developed a test harness to run Stagefright on a beefy machine. And then I would periodically, like say once a day, I'd go and I'd stop the fuzzer. I would look at all the results, bucket them, I would analyze them, and then I would fix each individual vulnerability and I'd catalog it. As soon as I found it, then I'd restart the fuzzer for the next day. So basically every day I was guaranteed I would never find the same bug again. Oh, this slide didn't make it. Poor slide. So the length of testing, I think, for this one was about a week, maybe 2 weeks. With AFL, I was getting about, I think it was something like 3,200 executions per second testing this code. And so after a week of running AFL with this code, it said it ran for like 6 months or something on the time based on the multiplication of speed and cores. So the number of issues found in that second phase was something like an additional sort of like 6 vulnerabilities, I think. So then finally got to reporting them, cataloging them. Here are all the CVE numbers broken out with the MP4 atoms that were affected. And apart from these, I also reported a whole slew of stability fixes. My thoughts were fixing all these null pointer dereference bugs and other lame bugs. That's just going to increase my fidelity when I run my fuzzer. So the idea is to give everybody those fixes so they can run their fuzzer and have good fidelity as well, instead of sorting through a million null pointer dereference crashes. So let's talk about one of the bugs in particular that I thought was kind of crazy. So I don't have time to go into the full details. There's good write-ups out there already based on media coverage. People have looked and wrote them up. The patches are already out there in several forums. And also the commit messages that I sent in were very good and very clear commit messages. So it should be clear what's going on in each of them. So let's look at a few interrelated issues. We have this commit back from July 28th of 2014, which is about a year ago. It's right before Black Hat. Thank you. This is right before Black Hat last year. So the guy committed this. It's a sample table check integer overflow during table alloc. He gave these bug numbers. So let's look a little bit closer at this. They're all really similar, so we'll just look at one. They're basically the same thing. Here's the added code with the pluses on the left. You can see that we have a 64-bit unsigned integer. We're going to multiply this stuff out, and if it's bigger than 32-bit maximum, basically size max, then we're going to say, that's a failure, out of range. We're not going to let it go down to this code that follows where it would actually cause an integer overflow and allocate insufficient memory. So it looks good, right? I thought it looked good. I saw this go into AOSP. I was like, they fixed that one. Oh, man. So it's embarrassing but educational. So it sort of is a fix, but it's not a fix. And here's why. So in C, if you multiply two 32-bit numbers together, you get a 32-bit result, even if it's assigned to a 64-bit number. So there's no way for the compiler doesn't go, you're assigning to 64 bits, so that must mean you want a 64-bit result. It's not that smart. So the original vulnerability remained exactly how it was. And like I said, I thought it was fixed. And when I ran the fuzzer, I was like, why is this coming up? I thought it was fixed. But in fact, it was not fixed. So let's talk a little bit about exploitability real quick. I know this is a bit of a hot topic. So many of these are, out of the, I think, 10 CVEs that I listed before, there were, I think, 6 that result in direct integer problems that lead to memory corruption in the heap. These kind of issues have been proven exploitable multiple times, especially in C++ code, but Android mitigations do come into play here, and we'll show that a little bit later here. As a note, diversity in the ecosystem, because there's so many devices and different patch levels, there are addresses that you might need from all of them to make an exploit that works on all of them. But I don't think that's an unsolvable problem. I have a lot of firmware on my server. I've got a lot of devices I can test directly. So, if you build that kind of lab, it's not really a barrier, I don't think, at least that part. So let's recap media server just a little bit. Some of the things help us and some of the things hurt us in exploitation. So spawning from init, that means that when the process restarts, it re-execs the process so that it gets a whole new address layout. It's all randomized again. So even if you were to leak something that, say for example, you're able to leak some memory contents to yourself, if that leaking to yourself caused the process to crash, that information you just received is pretty much worthless. So that also means that the Zygo ASLR weakness, which was well known because they only fork, they don't exec, that means all apps have the same address layout pretty much when they were born at least. So because it also because it's spawned from init and it restarts, you can try your attack over and over and over and over again. The limit on that is really depending on your attack vector. So with MMS, you can just go until, whenever. With like an SD card, I don't know if you want to insert and remove an SD card a whole bunch of times, but you probably could do that. And so also because of it restarting, you can use that to your advantage to bypass ASLR through sheer brute force. You can just keep trying until it works. One other thing is that media server is a multi-threaded process. And one of the things I found in writing the exploit here was that because it's multi-threaded, there's some determinism problems with the heap. I've been able to work around a lot of them, but not all of them. So new in Android 5.0, they had a new mitigation. They also had a change to JE malloc. So these two blocks of code are functionally equivalent. You can see that it's like new sample to chunk entry, and so on. And then that's the same as basically mallocing the size of one thing times the thing in the brackets, the number of elements. And so the Android compiler team in 5.0 decided they were also going to switch to GCC 5.0, which is great. It's always nice to upgrade your compiler. I think I got this like out of order or something. There's a slide missing. So the mitigation, basically what it does, this new mitigation in GCC 5.0, is when this multiplication happens, it detects whether or not that multiplication is too big to fit in a 32-bit number. And if it is, it changes the size of the allocation to the maximum number. So it tries to allocate like 2 to the 32. That typically does not work out very well, and so that leads to usually a process crash. So here, let's look at a mitigation summary, because mitigations are very important when it comes to exploitation. When you're determining whether a vulnerability exists or not, it's not really that important. But when you're talking about what is the actual risk, the more practical risk, mitigations are important. So SE-Linux in this case, and we're talking about the MMS attack vector in this case, it doesn't come into play at all, really, unless you're already in. So the attack is coming from remote, so there's no way that they can really label that, because it's just coming remotely. And it's doing what it's supposed to, right? It's doing design behavior. It's not you trying to cross a boundary that you're not supposed to. Stack cookies are not at all relevant here. They're not applicable because we're not talking about stack corruption. We're talking about heap corruption. Fortify source, again, not in play here because it's a dynamically allocated buffer, and Fortify source cannot track dynamically allocated buffers. So ASLR is there, but it's only there from 4.0 and later, unfortunately. And we'll look at that a little bit more. So, but NX is there. It's been there for a long time. But the thing with NX is if your ASLR is weak or you can bypass it in any way, then you can just use ROP to bypass NX. It's really not a complicated jump there. So the GCC new mitigation, it only affects some of these vulnerabilities. Basically, it will only affect those vulnerabilities where the number that's inside the brackets is a simple number, and some of these vulnerabilities actually are like taking two numbers that you can control, adding them together, and those are inside the brackets. So the integer overflow there would actually occur before the multiplication with the type happened, and you can still trigger a problem. Okay, so ASLR. ASLR is address space layout randomization. It's definitely the biggest challenge. It's basically the only challenge to exploitation. So I managed to, I fully partially bypassed it. Wow. So yeah, so I fully bypassed ASLR on Ice Cream Sandwich. There was not an issue there because on Ice Cream Sandwich there was a known weakness in the ASLR implementation that left both the binary base and the linker mappings, executable mappings, at a predictable address. So I think this is really also possible on newer devices. We've been talking, a few of my friends and I, and cohorts in the industry here, about ways we can bypass ASLR even on newer devices. My biggest guidance here would be 64-bit devices. 64-bit makes a big change. It's not really like something you can say like, oh, 64-bit is a mitigation. I don't really think that's what it is, but it definitely makes ASLR more effective. So exploitability by release. Gingerbread, yeah, you can exploit it. There's not really ASLR there. Ice Cream Sandwich. Yeah, I mean, I didn't go into Froyo. I didn't put Froyo here, but Froyo you should put in the same bucket as Gingerbread. There's not really anything going on back then. Ice Cream Sandwich, yes, proven. It has weak SLR. The newer devices, in theory. More to be found on that, right? So I think I have like 3 slides left or something. Well, how much time do I have? 2 minutes. All right, I think the video is like longer than 2 minutes. No, I'm just kidding. I cannot find a way to get out of the screen. Is that like BS or what? Anybody know a key to show your desktop on OS X? What's that? Windows, are you trolling me? I mean, I think that works on Windows, but it doesn't work on OS X. Command D, that's what I did. Windows and Command are the same button, right? What am I getting here? Thank you. Bookmarking my own presentation. Okay, this might actually work. Oh no, that's not gonna work yet. So let's try escape over here. Oh yeah, there we go. Right there, let's do it. All right. Now we're gonna have the problem again because I'm maximizing it. All right, so here's a little video. I would do a live demo. I didn't have time to set the live demo up, although I have the equipment with me. Here, let's see if we can get some audio. I'm gonna take this down here. Where's the mic? Where is this coming out of? Can you guys hear the audio? If you guys like this music, you should come see us on Thursday at the Z Party. Oh, thank you. So we're going to do it one more time, just because, the screen is off, and what happens when the screen's on, right? Maybe you're looking at your phone. What will you see? And this is just my exploit. This is not the ultimate, penultimate, amazing, super dev'd out for like 5 months exploit. Don't mind the typo either, if you can spot it. There it is. Okay, thank you. How does this thing work again? You clicked it on me before. Like this? Just, okay. All right, so let's see if we can get the slides back now. All right, so that was the demo on ice cream sandwich. You see it worked the first try. I'm going to be full disclosure with you guys. It works every try, but not every try the first try. So that took a little bit of extra time to get the first try. On average, it was like the third try maybe. And that's because of the heap determinism stuff I mentioned before. So what about getting these issues fixed? I'm going to go super fast now because I got like basically 1 minute. So I reported all this stuff to Google in like batches. In the middle, I reported to Mozilla, and then like throughout April and all the way up to June, I reported them to BlackPhone through BugCrowd, which was all great. So I requested embargo from everyone. That was basically a giant shit show, and excuse my language, but it was terrible. The Mozilla guys pushed the patches into their code branch without ever saying anything to me. Like the BlackPhone guys were great. They were like, hey, do you mind if we ship binary fixes? I was like, go for it, ship binary fixes, just don't mention anything. The Android guys even like dropped some patches like without letting me know what's going on, and it was just a big mess. When I reported to Mozilla, also there was another team who reported one of the bugs I already knew about and was going to report to Mozilla like 2 days later, and so their bug actually became a public advisory about Stagefright in Mozilla. I was like, that's great, thanks a lot, guys. So I gave everybody 90 days. I was like, hey, we're going to aim for about a month before Black Hat because that's a good time. Our policy as Imperium is 30 days. We are very aggressive. But in this case, mobile ecosystem, Android, 90 days is like, come on, you guys might be able to do it. Go. And they did hit some of them, so that's good. So everyone was great to work with. The Android guys, when I sent the patches to them, they were like, thank you. They're applied, thank you. Thank you for helping us make Android more secure. And I'm like, that's so nice. They did all their work to notify everyone. I mentioned, so Mozilla also shipped the fixes in 38. And we created this Imperium Handset Alliance to try to help improve our disclosure process, but also communication between everyone. And we recognize that people like BlackPhone, they're not getting notified. And so we're like, well, we'll just notify them whenever we have stuff or whenever we figure stuff out, just to keep them in the loop. So at this point, we have over 25 carriers, manufacturers, vendors involved in it. It's only been going on for 3 days now, I think, or something like that, three or 4 days. So update deployment, it's still going on. You guys all know of some media coverage and the long stories from days of old that this has been going on. However, there's 2 new late-breaking things that happened this morning that Adrian Ludwig, lead for Android security, announced, and that was that both Google and Samsung are going to a 30-day patch cycle, very similar to the way Microsoft does their Patch Tuesday. So that's pretty awesome. I've also heard some rumors that there may actually be patches for Stagefright for devices older than 4.4, depending on who's supporting them. Yeah, I can't say anymore. I don't know anymore. So conclusion, what am I trying to say? I don't know what I'm trying to say up here. And I'm sorry I took the whole time. Am I actually out of time, or do I have so the second 10 minutes is up? Clear, right? Okay, GTFO now. Okay, I got it. All right, so Android's code base probably needs more attention. This is probably not the only code that's been written in perhaps a hurry, or that may have issues that are low-hanging fruit. Mitigations are definitely not a silver bullet. We've seen mitigations, new ones, old ones, things getting introduced, and pretty much every time somebody's bypassed it in some way with some bug. Maybe not every bug, but some bug eventually. You only need one bug to write the exploit, or maybe two, or maybe three, but anyway, you don't. So vendors need to be, and they are, thankfully, some of them, being more proactive, maybe not so much, but they're doing more aggressive deploying of fixes, and that's awesome. If you guys are interested in more about the changes that have been going on and the things that, I don't really want to take entire credit for spurring an ecosystem, because I think that they have been kind of building and been in talks for a long time on some of these things, but hopefully the seriousness of these issues has kind of lit a fire under people's butts, if you will. So thanks for your time. I don't, I guess, have any time for questions, but you guys are all welcome to ask me any question anytime about this or anything else. It's all good. I'm a human and I like to talk to people. So say hello.